All right. Well, class, this is calculus class here. I'm recording this for the people that are absent. So let's jam. First of all, let's go to the beginning of it all, which was, I think, like right here somewhere. Let's see. That's still homework. That's still homework. And that's really just to scare Elijah, who's sitting in today. That's what this is for. Okay, there it is. So hyperbolic functions, right? Hyperbolic trig functions in particular. We learned the fact that it's not from a unit circle, it's from a hyperbola, hence the name. And it is just the position of the x and y coordinate on a hyperbola. And so there it is. The interesting thing about it is a trig function can also be an algebraic function in a sense. So it connects with that right there. So wow, how interesting. And so then we want it from there. So this is going to be part 2 here. So the graph of those look like this, and then we connected them by the fact that they do connect at the, let's see, how would you say it here? At the ends to these exponential functions here. So we were able to make curves of them. Let's see what else we did, just to remind ourselves here. So we did definitions for each of those. Hyperbolic sine, hyperbolic cosine, hyperbolic tangent, or actually no, hyperbolic sine, hyperbolic cosine have connection back to exponential functions. And the rest are built out of relationships there. So that's cool. Okay. Identities. Not all the identities from trigonometry hold over. I mean, like they do, yes. But we're just going to consider the ones needed for calculus. So there it is. So sine is still, hyperbolic sine is still an odd function. Hyperbolic cosine is still an even function. That's cool. And then this relationship called Pythagorean theorem holds except for a minus now in between them instead of a plus. And so again, these relationships hold. And it's the addition rule for hyperbolic sine and the addition rule for hyperbolic cosine. Notice it's the functions are exactly the same. The sign has changed slightly on this one, particularly on the cosine. Anyways, that's kind of what we got to here. And we got to derivatives last time. We just didn't get to integrals. And so I think for the homework, I think I said you guys can probably do like 1 through 13. And then at that point, you do have to sort of stop because we didn't cover the rest. So now we get to cover the rest, which is super cool. Okay, and then we have the derivative of hyperbolic cosine. And so real quick before I go on here, is that okay? Yeah, the derivative stuff. Okay, it was good. Okay, so let's jam. We have to do 2 things here. We have to do integrals. Oh, sorry. No, sorry. I'm in a different headspace here. Now let's go to slightly interesting function here. This is going to be called inverse function. So we mentioned it already before. So this is part 2. Let me do part 2 here. So I have it for my notes. Part 2. So that derivative is taken care of. Great. So now the question is, what is, we should even label this inverse. Oh, you know what? Let me erase this to the way I wanted to write it with my little different draw pens here. So part 2 of hyperbolic functions. Okay, boom. So back to definition real quick here, just so we have ourselves all we need. So back to this little piece right here. Hyperbola comes across this way, just to make sure we got it. Because when we do, when we learn something, it's interesting. Oh, T, I want to write T in here. So this is just how far you are away from the 1, 0 marker. And so remind ourselves what in the world this means right here. And I'm going to draw some other colors here. This right here first. So I'm going to go like this right here. This little gap right there. And I'm gonna just kind of color it in. Okay, what in the world does that mean? We'll talk about it in just a second here. So we have that on our hands. So whenever you learn something, obviously we're kind of creating synapses in our brains, and sometimes we have to sort of hear it again in order to sort of put it into our brain. So the question is this. This is our definition of hyperbolic cosine, hyperbolic sine. That's great. Except now we want to go backwards. And so just like we did in trigonometry, we say to ourselves, okay, hold on. So y is equal to, let's do cosine, that's fine. Cos of t, like that. Or of x, because we want to. So real quick here, just a few things that we need to lay out here. So t is, remember, this is how far you are away from that little piece there, right? Just like the unit circle. And so what we do is we make it eventually into graphs, right? For cosh, it's this graph right here now, right? This is hyperbolic sine. But now we've got a relationship between x and y. That's what we want to have. Okay, we're good? So we're kind of setting a few things down. So here's what we want to do. We want to go backwards on it. So just like trig functions in trigonometry class, we were able to do the inverse function. We're going to do this in the inverse function here. So what do? We switch x and y first, just like we used to do inverse functions. And then we're going to inverse the cosh out of the right-hand side. And when we do that, we create a inverse hyperbolic function. Whoa, crazy. And so we set it up as y is equal to cosh inverse of x. And there it is. There's our hyperbolic inverse function. The question, first of all, before we even go on to the derivative stuff, is what in the world does this mean? So I know off the unit circle. So let's kind of take a few little roundabouts here. In our original trig function, if I were to write this x or cosine of t, let's keep it the same values here. Sine of t. So when we do that here, we understand that that t value is just how we wrap around the outside of the unit circle, right? And that piece had a connection back. Remember how the t value had a connection back to theta, right? It was the radian measurement off of theta. Theta is an angle for us, but t is a real value, and that real value is the distance away from 1, 0 on the unit circle. So again, I'm just trying to put trigonometry and then this stuff together. Okay, so what do we do from there? We made this into x and y, so we started graphing cosine, because cosine actually can have a relationship outside of the unit circle, right? Remember that? We went to there. The logic progression from trigonometry here. And so now we connected the x and y on a different coordinate plane, not the unit circle anymore. We connected it on y is equal to cosine of x and a relationship between x and y. So far, so good. And then we said, you know what we're going to do is we're going to take the inverse. So instead of going from x to y, instead of an input being the x, and the height, really the y value being the output, I switch my x's and y's. I solved for y, and I got myself I created an inverse function. We good there? Just want to make sure that we're connected here. So then the question becomes, inverse function, remember how we had to chop up the domain? It had to pass the horizontal line test. Do you guys remember that? In order for the inverse function to be a function, in order for that guy to actually be a function, we had to chop up the our domain just to be only here. This was our domain for cosine. Damn, this is going all the way back to trigonometry class. Hope you guys remember that. Because notice it spans all the way from 1 for cosine all the way to -1. And so that's all the values I need, and it has to pass a horizontal line test as well. Right? So there's that piece. Okay, is that jogging some memories back?
Would it not go through a whole period of cosine?
Not for inverse cosine. Yeah, so we had to chop it up in order. So let's jam. That's why we ask questions. That's why we go through this process here. So you guys please do. Let's take a side real quickly here. So in order for something to be a function, it has to pass a vertical line test. We good? Good there?
Yeah.
So does this guy pass a horizontal line test? Absolutely, right? Yeah, because I can put vertical lines coming straight down and it's not going to hit at more than one spot. That's cool. Everything's great and dandy. Then what we do is we move on to the inverse function. What we're going to do is we're going to flip x's and y's around. So if you, and this one I probably didn't show you in trigonometry class, if you were to keep all the x's and y's together, remember we're flipping x's and y's, right? So this dot here now becomes 0, 1, now becomes 1, 0. This dot here becomes 0, 1. I'll just write it like that. So, and then this guy here all bounces all the way down to here. Is that right? So if you were to graph cosine, this is going to be so crazy. You guys ready for this? If you were to graph cosine inverse, it'll look like this. Good there?
Yeah.
And so what we want to do is like, oh man, that's not cool. We need to somehow chop this up so that, and I'm going to go back and forth here real quick here, and chop it up so that we can pass the vertical line test on the right hand side. And so what we do is we chop this piece here off. So that's negative, positive. So positive, negative. So that means we chop off this little piece right here. Let's see where we're at here. So that means we chop off this little piece. Good there. So we still chop some more. We chop this way and we chop this way. And lo and behold, I'm getting somewhere. Good there. So if I chop this piece now, essentially what I'm doing is I'm chopping this piece. And now the question is this. Now does this pass a vertical line test? Absolutely. So that's so cool. So now we have ourselves so real quick, I'm going to change x's and y's, but this is a totally different graph, right? These y's are not connected to each other anymore. This guy is a inverse cosine function. We're good. Sweet. Okay. That's super cool stuff, guys. Okay, so now let's talk about it. So now let's go back up here. So when we create this inverse function, the question then becomes, what is it actually trying to say if we're thinking about the unit circle? If we go back to the unit circle, what are we trying to do with the inverse function? With the inverse function, we're going to go from t back to, instead of this little coordinate, let's say x right here. X is equal to cosine of t. We go backwards on it, or we become cosine inverse of t becomes x. We good there? Oh, sorry. I messed up on my variables here. Inverse cosine of x becomes t. There we go. Better. So we're just trying to get to somewhere here. Or we can say like this. You guys tell me if this is correct. The x value right, the x coordinate of this was theta, cosine of theta, right? If I take the inverse function, would I say this? I'm going to say cosine inverse of x becomes theta. So notice along a unit circle in trigonometry class, what we're doing with the inverse function is to go back to the angle measurement. That's what we're doing. We're going back to angle measurement, or we're going back to our radian measurement around the unit circle value. Okay, are we cool like that? So now the question is this. What is the inverse cosine doing in this value over here? Or what is a cosine inverse doing of, what's the connection here? So I want to just draw the connection here. So let me do this here. So if you were to take the inverse of this, what happens is it's calculating the area right here. That's the little red stuff. In fact, it's half the area. That's what an inverse function does. Because then it's like, what in the world does the inverse function do? That's what it does. It calculates the t value connected to the area that is left. And in this case, again, t value connecting to the area that's left, or half. It's actually technically half the area. We, in our mathematics, we technically say it's kind of like this right here. It actually calculates this area too, or we just say half the area. So we can actually just be only on the top value. Okay, so again, just show that's what a inverse function calculates as opposed to an angle measurement. Now let's see, what is the definition form? Oh, and then real quickly here, let's do this here. Sorry guys, got to jump back to our graphs for sine and hyperbolic sine and hyperbolic cosine. Let me jump all the way back to the graphs for them. And it was like here. Just trying to subtly connect pieces here, okay? So notice what we had to do here is we had to limit our domain in order to make the inverse function a function. We good? We got to do that with sine anyways. So this has to pass, oh, you know what? Interestingly enough, look at this. This has to pass a horizontal line test for this to pass a vertical line test. Are we good there with the connection there? That is so cool. So if something passes a horizontal line test as a function, then its inverse will also be a function. Otherwise it's not, because we're just switching x's and y's. Again, a lot of mental math here, guys. And if you're keeping up, you're doing great. So now let's go back to our hyperbolic sine graph. Here it is. Here's our hyperbolic sine graph right there. Question, does this guy pass a horizontal line test? In fact, I'm going to even do this. I'm going to take this and I'm going to, first time doing it, let's see what happens. I'm going to bring it over here and make it smaller. Okay, we're good there. There's our graph of it. Does this guy pass a horizontal line test? Absolutely. Is that right?
Yeah.
Absolutely does. Look at this. We can crunch this out like this and everything's fine. Good. So then the question is, can I graph this? Yes. All I have to do, get rid of this S. We don't need that. All I have to do here is switch my X's and Y's. Good there? And when I do switch them, this is what the graph looks like. And it's going to go something like this. It's going to go in like this and then kind of out like that. And it's going to go on forever because this guy can go on forever. It's just going to, this guy continues to go like this right here, and it continues to come in slowly. The same thing here, right? It's going to hug this asymptote, and it's going to come in slowly. So now the question is this: how do I, or what's the formula of this guy? Oh, hold on. our hyperbolic functions have an algebraic component to them. Is that right? They are e to the x plus e to the negative x over 2. So if I am to undo the work here, I have to do some algebra. And the algebra gets really complicated too, so we're not going to go on that. We're good, but I want to give you the formula. So then the question is this. It's almost like this. What's the equation for this line right here? What's the equation that makes that line? All right, and here it is. The equation that makes that line is hyperbolic inverse of x is equal to ln x plus the square root of x squared plus 1. Done. Wow. So yeah, it does make sense because we're undoing e to the x. So we're going to have an ln feature inside it. Okay, cosine does the same. We have graphed cosine, so let me grab it from the previous slide. Okay, are we good there? And this goes on forever, so we should put arrows here, arrows there. Okay, just getting ourselves to the maybe we might actually, yeah, we can do that. We're honors calculus. We can make that. We'll actually go and make the formula for it here. Okay, let's go cosine. Let's do cosine and then we'll jam with tangent. Let me go backwards up here and let me grab this guy here. This is the hyperbolic cosine right here. Copy. Ooh, I wonder if it's going to copy well. No, almost copy well. Okay. I'm going to graph hyperbolic cosine. We good? So this way, and hyperbolic cosine goes like this. It touches at 0, 1 and comes back up. Okay. Does this guy pass a horizontal line test? It does not. No, no, no. That's no fun. And real quick, are you guys comfortable with the graph for this guy? If you need to see it, it's on page 255 of your textbook. All right, that's where we got it from. Good there? Definitely does not pass a horizontal line test. So now at this point, we do have to limit our domain, just like we did for cosine in trig class. Where should we limit it? I'm going to just chop this off right here. I'm going to chop off this whole entire negative side right there. Good there. Yes. Okay. Then I'm going to switch my x's and y's. I'm going to graph this guy. And the graph looks like it started off at 0, 1. Therefore, on my graph, it's going to start off at 1, 0. And it kind of just folds up. So this guy's just going to fold sideways a bit. And it's going to kind of come off like this. Okay, what is this guy? Y is equal to, let me write it again here, boom, goes to, switching x's and y's, right? The whole thing that we do, right? Switch x and y. Solve for y. And we have ourselves y now is equal to inverse hyperbolic cosine. How about that for, say that 5 times real quick. Just kidding, tongue twister there. Okay, so now we have ourselves a little issue though. So we have ourselves the fact that we limited domain here, is that right? So we're gonna have to limit the domain here. So we're gonna say, look, we're only gonna look at stuff that has x greater than or equal to 1, just this little piece right here. Okay, now the question, what's the formula? What's the formula for this? So I'm kind of interspersing two things here just to make sure we're not confused. So this guy gives me the graph, is that right? And now I want the formula in terms of x. I want the formula in terms of domain. Okay. So then y is equal to this, and then cosine or inverse hyperbolic cosine, what's the algebraic formula for it? Is this right here. And by the formula, boom, like that. So with tangent, we could actually put x's and y's, we could put hyperbolic sine over hyperbolic cosine on top of each other, right? And if we do that, there's some algebra, but I want to give you that formula as well. So y is equal to inverse hyperbolic tangent is equal to 1/2 ln of 1 plus x over 1 minus x. And that is very limited range. We're only going to go from -1 to 1. Okay, good. Just for you guys to be able to read the textbook is all I want you guys to sort of maybe take the time to look at. Let's see, we have time, yeah, to look at the derivation of this one. Not all three, but how about this? So so the question is, how do we derive this? How do we derive this from here? Like, how does that even happen? Let's do it. So let's go with it. Show, boom, boom. Now, exercise what? Exercise. So just jumping back and forth a little bit here. Identities. We didn't have an exercise. I think this would be exercise 2 then. Exercise 2. All right, let's go with it here. Show that hyperbolic inverse sine is this formula right here, is equal to ln x plus the square root of x squared plus 1, close it off. We're going to show that to be true. That is crazy, but cool. Okay, so put your thinking caps on. Let's kind of work through it here. Please ask me the question, like, I don't know where you get that step, right? Because it's a proof. So it's things that we know, we come together, we put it in, and we arrive at something here. So here it is. So this is kind of cool because it's actually a real proof that you would normally do. So let y is equal to sine hyperbolic inverse sine. And logical flow. Let's go with it here. So again, it's going to either come from a definition or a formula, right? That's what we're working with, or algebra. That's how this is going to flow. So if that's true, then is this true then? If I take the, y. Everybody agreed there. Okay, I just kind of moved it to the other side. I made it back into the original hyperbolic sine function. We're good there. Switch it around. I'm going to say, okay, that's true. Then this is also true. And if that's true, then let's go to our algebraic definition for hyperbolic sine. I think it is e to the, now our variable is y this time. So it's e to the y minus e to the negative y over 2. You guys check me just to make sure. It's a minus sign there, is it?
Yeah.
Okay, for definition. Okay. Cool. Okay, so if that's the case, let's get rid of the sign, the whole middle section here. Let's get rid of this. Let's just do that right there. Good there. Let's multiply by 2, and we get ourselves this situation. And let's see, let's move the 2 over, the 2x over. So this is 0 is equal to e to the y minus 2x minus e to the negative y. That's cool. Set equal to 0. And so now the question is really, what are we solving for, right? Notice that our y value is still equal to inverse hyperbolic sine. Is that right? So technically, we're just solving for y. Can we solve this guy for y? And if we have ourselves our algebraic definition of hyperbolic, inverse hyperbolic sine. Okay, let's keep on going here. Let's see. What should we do? What should we do? I think I can do this here. I'm going to multiply both sides by e to the x. This is cool. I'm going to multiply this guy by e to the y. Sorry, e to the y. Multiply this guy by e to the y. And again, we're just deriving the formula, right? Cool. All right, so what's going to happen here? Let me back to my black pin here. So that means I still get a 0 on the left-hand side. I get e to the 2y minus 2x e to the y, the multiplier across. Then this one should just become a 1. Is that true? Okay, I'm just going to do this real quick here. I'm going to just switch the 0 where the 0 is. Oh, I can do 2 things here. So that little 2, if you have exponents, right? I can write it as 2y, I can write it as a multiplier, or I can just write it like this, right? This is this guy to the second power. True, true. Then we can write minus 2x. This guy is to the 1 power. Minus 1 is equal to 0. And so let's see, does this look like a quadratic formula? Yeah, it looks like something squared, right? Minus that 2x is our multiplier, but here's our variable. Our variable is this little 2y. So something to the second power, something to the first power, and then not that something at all. And so what we can do, we have ourselves the quadratic formula. So I'm going to say e to the y is equal to, you guys have to remember the quadratic formula, negative b plus or minus square root b squared minus 4ac over 2a. So you got to think back, okay, where was that? Yeah. So negative b, I think I can write it. So the quadratic formula, if we were having to solve for x, would have been negative b plus or minus the square root of b squared minus 4ac over 2a. But you guys are calculus students. You guys have memorized that like crazy already. So opposite of a middle term, so negative of a negative 2x is a positive 2x, plus or minus the square root of that thing being squared. So 2x being squared makes 4x squared minus 4 times a, which is 1 technically, times c, times c, which is the negative 1, all over 2 times a. Okay, so if I got this right, I have myself a 2x plus or minus Ooh, guys, check this out. There's a 4 inside here, isn't it? So actually, I can pull out a 2 out of the square root. Leaves me with square root. Oh, it's a +1, right? It's plus right here. Sorry, guys, to make sure. +1 over 2. And what can I do with the 2's? I can cancel the 2's directly, except I have to cancel with every single term on top. We good? Or the sophisticated, correct mathematical way of doing it is you factor out a 2 first. And then you cancel off the 2's on the side. We good? So quick method or the proper mathematical method of doing it. Okay, so what are we left with? And the one thing we have to sort of see it here is if that little minus sign, you know, Pythagorean theorem has a little minus sign. No, the quadratic formula has a little minus sign right here. All right, the only problem is, do you guys remember the graph for e to the y? If we were to graph this guy, remember how it never touches 0 and it has to always go up? Is that right? So in this case, what happens is the same thing happens here. This guy cannot be a negative. You can't have a minus sign because it can't touch 0 and it can't be a negative. So we're going to drop the minus sign from our graph. And so we have ourselves this. The y is equal to x plus the square root of x squared plus 1. Good there? Yes, and I think we've got it. How do we undo an e? I think what we do is we put ln in front of it, right? ln on one side, ln on the other. Anyways, just want to take you guys down a little proof road there. L and E cancel off each other. We get ourselves, that is pretty cool. And then hold on, what was y equal to initially? That's what it was equal to. Perfect. Boom. We derived the formula for inverse hyperbolic sine. Are we good? Super cool.
Back at the first step, how do you strike one there so that you line up that half the quadratic
Oh, right over here.
step that you right from one step to the one.
Oh, for which one? For right here?
Yeah.
Oh, gotcha. Yeah. Yeah, sure. Let's go with it here. Absolutely. Guys, this is why we're here. So if we label our ABC, there it is. So there's my label. That's my A value. There's my B value. And there's my C value. No problem. No problem. Okay. There's that jamming. We're cool. Okay. So now let's do, oh man, this is not far enough. Let's do derivatives now. And then let's go with it here. Let's start deriving things. Okay, so that's the definition. Now the question is, I'm just going to list them for you guys because we're kind of getting close to running out of time here. So derivatives of inverse hyperbolic functions here. They are in the textbook here. We'll just write them so we have them in our notes. Oh. Derivatives. Inverse. All right, a whole mess of them, right? There's 6 of them here. So here's what we got. The derivative of, and I like to use brackets because it kind of gives you, the book uses parentheses. Most math textbooks, I would say use brackets. And there it is. This is interesting stuff right here. That is it right there. As you derive, and we can make, just don't have time here, we can actually derive the formula for it if we need to. But there it is. Remember with ln takes the bottom half into somewhere. So we can derive it that way. Okay, let's list all 6 of them real quickly here. The derivative of inverse hyperbolic cosine. All it is, just in a different spot here, it just has x squared minus 1. There it is. I think I can probably squeeze in the derivative of hyperbolic tangent. Inverse hyperbolic tangent. Come. Over x squared. Should be a 2 there. X squared. Good there? Elijah, tired of writing. I'm done. We'll do an example. You can write that one down. Okay, boom, boom, boom. Got 3. Got 3 more to go. And then we'll do some examples here. So inverse hyperbolic cosecant. That one gets me a -1 over the absolute value of x times the square root of x squared plus 1. Whew. The derivative of inverse hyperbolic secant. Of x, should be x, equal to -1 on top. You don't need the absolute value in this one. And you're going to have x squared right there. And last one, the derivative of inverse hyperbolic cotangent. Gets me all right, and some funny thing you should sort of see here. Notice inverse hyperbolic cotangent. Notice inverse hyperbolic tangent. Okay, how fun is that? They actually have the same exact derivation. They have the same formula. Okay. Jamming with that, let's do now example here. This is example 3, last example of the day. So the question is, can we find the derivative? And of course, I'm going to just throw a whole bunch of trig functions at you. Find the derivative of inverse hyperbolic tangent of sine of x. Talk about meshing things together here. All right, give you guys like a 1 minute here. Try yourself first, go for it, and see if this makes sense as well. Pick it up from the textbook here, but if you see if you can do it by yourself. All right, let's try this thing then here. So we're going to go with the derivative of inverse hyperbolic tangent first. It's 1/1 minus x squared. Goes x, of course. That's right. Absolutely. So we're going to go 1 minus, but this one's going to have sine of x being squared. Then we got to take the derivative of sine of x, right? We still have that to take derivative of. And so we do this. Derivative of sine. I'm gonna go with cosine, right? This is back to our trig formulas, right? This is cosine. Oh, cosine can actually just go on top. This is cosine on top. Hey, this is 1 minus sine squared of x. I've seen that before. I think that's like a Pythagorean formula from way, way back in trigonometry class. What is 1 minus sine squared x? So don't get confused. I put teaching calculus students here. The one thing that has, we start meshing the inverse sines with the regular cosines with the hyperbolic sines all together. So, cosine squared, absolutely. I think I can maybe just. Now this is cosine of x over cosine squared of x, which makes 1 over cosine as they cancel. One of them's canceling. And then we get ourselves a good old secant of x. There it is. Thumb through if there's any other major ones here. Tangent. Yeah, I think that should go good there. I'm going to intersperse sine with regular sine, some algebraic functions as well with it. Maybe one more. Let's see, we got 5 minutes. Yeah, one more here. So 3. So this is 4. Let's go with 4. So sorry, Elijah. We have one more. So then take the derivative of this. Let's see, they're all interspersed in here because you have hyperbolic derivatives, right? And then you also have inverse hyperbolic derivatives here. So let me. Okay. All yours with that. There's a condition on secant because there's a condition on cosine. So the condition is that it does have to be greater than 0. That's the only condition for. All right, let's look at our rules here. And again, this should just be a chain rule again. You guys help me out here, making sure we're doing everything correctly here. Derivative of secant. It's going to be a negative in front. It's going to be a minus sign here. It's going to be x, which is actually the square root of 1 minus x squared, multiplied by the square root of 1 minus the square. I'm going to square it out already here. We could put square root in there and square it. Times the derivative of the square root of 1 minus x squared. Okay, this gets heavy. So let's keep on going. What's that going to give us here is a algebra form here. 1 minus that plus that. And the derivative of this guy, this is algebra now. So this would be multiplied by, let's see, 1/2 because of the square root minus x squared, negative 1/2 multiplied by negative 2x. Okay, is that good there? You guys check to see if there's any mistakes there. We've got a minute left. I'm going to do like this, yeah. Take it to the next. Don't even want to copy all that down. Okay. Waiting for you guys to finish up copying if need be. Okay, and you guys finish it off if you need to. Can you simplify that? Simplify that with exactly a minute and 5 seconds left. So let's see what I have here. I have 1 over a little negative in front. This little square root by itself. This one's actually going to give me negative 1 minus 1 is going to be a square root. This would just be a square root of x squared, which will be just x. See, those 2's cancel. So let me go like this here. So that 1/2 and that 2 with a negative. Hey, there's a negative of a negative. So that's actually going to cancel there. So I'm going to erase that little negative there. I'm going to delete that because I've got that positive now value. I have an x on top that's flowing nicely here. So that x still on top. And this guy becomes a square root of 1 minus x squared. Is that good? It moves to the bottom. So please ask me the questions here, because in calculus class, what happens is it's the algebra that's the difficult part. Taking derivatives is not that difficult, but simplifying stuff sometimes is most difficult. Okay, everybody good with all those pieces? Good there? Okay, we're past time here, so let's go with it here. So notice the square root, this piece and this piece, they're the same thing. So they're actually just going to be this right here in this little circle. The x is going to move to the top here, and square root of x squared just becomes x. So in this case, the x's are canceled each other, and we're left with this right here. Okay, boom. I think we're done. Okay, you guys should be able to finish up the rest of the homework from 3:11, and I'll be sending you guys a study guide sometime tonight. And enjoy the rest of your day.